we've also recognized today Professor Kathleen Kramer, President of IEEE, who joined us today. Welcome, ma'am. So it's a tremendous honor to address such a large gathering, and I would like to thank Dr. Joy Lasker and the committee of the conference to invite me. It's enormous honor. So, well, for many of you from outside the United States, so welcome to America, and I'm sure you'll enjoy this beautiful city of San Francisco. So my talk today is, certainly not so much about technology as about the opportunities that all of you in the RF and the microwave field have in front of you. So I hope I can convey some of that. So antenna arrays, probably to go back way into the 1940s or 50s, but I think the first major application was this FPS-85 electronically scanning radar at Eglin Air Force Base in Florida. And that, I think, had something like 1,000 elements. It was built in 62, burned down, and 69, I think, it was commissioned. And that was one-off. So that was the first major use of antenna arrays. And then, of course, probably the next one, which came in not in one-off, but in millions, was antennas for MIMO in 4G and then now in 5G. And now antenna arrays are getting already got into automotive radars and things like that, where the volume is not millions, but tens of millions, if not hundreds of millions. And they're also getting into phones, and now the volume is billions. So all of you know where to focus on. So the thing about antenna arrays, of course, is sort of typically in the radio range. Much of the activity today is probably from about 0.1 gigahertz to about 30 or 40 gigahertz. But it's also getting into IR and millimetric, into optical band, visual bands. I'm not sure products have emerged there, but there's a lot of stuff going on there. But today's talk will be much about the bands that we are familiar with. So in the lower bands, it turns out that partly because of necessity, we're dealing with a much more complicated channel. There's a lot of multipath, there's lots of other things going on. So simple antenna arrays don't work. You really have to worry about adaptivity and so on and so forth. And, but I think at higher frequency, certainly visual and IR, we cannot manipulate weights and adaptivity so well, so it still assumes planar wavefronts. So where are the applications of antenna arrays? I think I would put them in sort of 4 or 5 broad classes. Communications, in radio, of course, we're familiar with, and most of you work in, but it's also coming in acoustic applications. We find them sitting on smart glasses now. Also, certainly, it's coming in slowly into optical. And things like beamforming, diversity, capacity, which is, of course, the big hit for antenna arrays, surveillance. So these are the applications that we've in communications. In positioning and sensing, radar, radio, acoustic, and optical. And there we've been interested in direction of arrival or direction of departure of signals at an antenna array. And certainly its applications come in radar. And of course, in this whole area of positioning, we also want to use another leverage of time of flight. If we can measure the time of flight between a transmitter and a receiver, we get the additional value in positioning. Interference cancellation, I think, is largely anti-jump. And for example, there's been a lot of discussion about how to use that in cellular, but it's never really been effective for reasons I won't go into. So I think it still remains somewhat a military technology. And of course, GPS are receivers are very prone to that, but I believe in the United States, we're not allowed to use interference cancellation with GPS receivers for whatever reasons. And the last area, of course, is imaging. And so radio, of course, again, and acoustic, IR, visual range. So things like SAR, ISAR, intrusion, and then people use Wi-Fi and even cellular for intrusion detection, fault detection, and so on and so forth. So it's a rich area of applications. So let me talk about the application in antennas. And this is probably the first reason it is actually used. So it turns out that the problem with radio propagation is you have multipath. And multipath causes fading because we have destructive and constructive interference. So we send a constant rate signal as a transmitter. The receiver is going to get a very fading signal. Of course, when it fades up to normal, it's okay, but if it goes below, that really hurts us. So dealing with fading has always been a big issue. And it turns out that it was first discovered, the value of antenna was discovered by Marconi, I think 1905 in Halifax, when by accident he discovered that the transatlantic link he was setting up a second antenna, I think, and somebody observed that the signal on one link was poor, the other link would sometimes be better. So that was the idea of receive diversity. And of course, it's remained as part of communications, radio communications since then. It turns out that if you have two transmit antennas and one receive antenna, the channel exactly has the same independent, hopefully, fading response. But it took almost 90 years to figure out how to use that. And the first idea came from somebody called Wittneben in Zurich. And a few years later, a very nice idea came from Shivash Alamuti. It's called Alamuti algorithm, which was used in 4G and has been dropped in 5G. So when you have a diversity at transmit receive, you can mitigate fading, and the more the number of antennas, the better it is. Today, it turns out that, so we look at the amount of literature in this area, which I'm familiar with, probably, I would say, at least 100,000 papers and maybe 150,000 patents. It's a huge, huge area. But so things got very complicated, things called space-time coding, and a lot of my students worked on it. But a lot of those ideas have been set aside. And in 4G still has some of it, but in 5G we kind of got back to very, very simple ideas, only something called cyclic delay diversity. And there's complicated reasons for that, because when you do complex things, they add problems like complexity in decoding, or sensitivity to channel knowledge, and so on and so forth. So for all that work that went on, the world has gone back to a simpler world, which may be a good thing. So I'm going to spend some time on MIMO. So MIMO was really where antennas paid off enormously well. So the history is that I spent a long time in India, but I landed at Stanford in 1991, and I want to point to that Professor Gene Golub. So I joined with him as a research associate. And he had a project with DARPA. And the DARPA's project was that the Air Force uses, I think it's called rivet joint aircraft. And these would fly either over enemy lines or close to enemy lines and try and listen to radios on the ground. So I'm going into some history because how MIMO came. And it turned out that on the ground, if you have two radios, let's say 20 kilometers apart, they would not interfere because the propagation loss is very high, so frequency could be reused. But at 70,000 feet, 60,000 feet, when the aircraft fly, there's very little, the propagation is very beneficial. It's not R4, R-4 is R-2. You tend to see many radios, so it means you can't listen to any of them. So there was a long history of how to solve this. The idea was use antenna arrays. You can see that you see the antennas below the aircraft, and they would use the different directions of arrival. These are planar wavefronts arriving at the array to separate them and listen to them. But this had a long history by that time of theory, lots of PhDs, and the algorithms had some instability in them, mostly from mathematical. And Gene was a big name in analysis of math algorithms. So he had this contract, and there was some work done in the Bay Area, but it was classified, and I was not a citizen. So I was working with Gene, and my thought was I couldn't get to any real data, so I would build a prototype. And so we did this at Stanford, and we used deck phones and a 3-element array. I was always doing, in India, I spent all my time doing development, so handy at making things work. I bought circuits for mini circuits and put up an array to test it out. And outside outside Durand building, there's an open space, and we would find two phones about 30, 25 degrees apart, we would separate them. But they get closer, like 2 or 3 degrees apart, it doesn't work because it goes beyond the resolution limit. But one day it rained, and we moved the equipment inside, the antenna array, to a 3-element array. And one of my students, colleagues, was holding both the phones in one hand in the way to get away from the rain, and I was finding that it was separating them. So that was quickly answered by saying Multipath was doing it. And a few days later, the idea of MIMO came, and so a few calculations showed that it worked. And we actually had a little prototype. We filed a patent in 1992. Stanford thought it would be a very, very important patent. We invited a lot of companies, the story for all you guys, and everybody walked away saying it will not work. The reason was that, because of those days it was 4QAM, and I thought 10 antennas both sides, not very credible, but you could get out of MIMO what you can do with, say, 1 watt of power, transmit power, you will do with additional power in SNR, you'll require 1 million watts. And that seemed somewhat incredible. But I think finally, the whole thing got rescued by some papers came out of Bell Labs, and then the world began to take off. So right now, MIMO, there are 450,000 papers and 570,000 patent publications, means includes issued patents, also patents which are no more active, the whole lot, including, of course, patents which are filed. So it became a very, very large ecosystem. Tens of thousands of people have worked on it. So I was privileged to be a part of that journey. So again, going back to Gene, so when you don't know the channel, in MIMO you can still make it work. That is the beauty of MIMO, that it turns out things like transmit diversity, you needed to know the channel to make it work well. But you could make MIMO work without knowing the channel. And there was something called SDMA I'll talk about later, which needed perfect channel knowledge. So MIMO was the big advantage there. But then it gets complicated and it's more complex. So the way to do it was actually for the receiver to learn the channel H, do the SVD, singular value decomposition, send the three matrices there, send V back to the transmitter, then pre-code with V and receive with U. And I'm saying this because Gene that time was running a big group at Stanford, and he would call it as the SVD capital of the world because he was working on it. And he'd always tell me, Paul, like, there's no application of this beautiful idea. And I want to tell him, he's passed away some years ago, every second there are tens of billions of SVDs being done because your phone is always doing SVDs. So that is Gene. So something about the leverage of MIMO. It's in a 5G network, in a metro, dense metro, these are small cells. The median SNR on these networks is about 24 dBm, 23 dBm. So if you have and today 4x4 MIMO works in these networks, and if you actually ask the question saying, if you run the MIMO, it's very complicated to go in all the details, you get a 4x increase in speed up. Actually, it's then compared to 1x1. Actually, it's more in the case of when you look at outage and fading, but let's say it's 4x. And then ask the question saying, in order to get the 4x with the one antenna system, 1x1 system, what can I do? I can increase SNR from Shannon theory. Well, you have to multiply the signal level by 16 million times. And little higher SNRs, that's closer to the base station, you can multiply it, you need to multiply it billions of times. So it's a huge leverage. And of course, we go to, right now, 4 is pretty active, but we go to 7, or in fact, the 5G standard talks about 8, we may not get there quickly. Then, you're talking about the leverage of MIMO is all the power in one phone, what we use in the entire world. So it's a huge leverage. So I think that clearly gave multiple antennas a huge lift. So there have been extensions of MIMO, and the first idea, which actually goes back to 1980s, was to look at, we have an antenna array, and we have two users separated in an angle. Well, you can, like the Air Force was trying to do, you could receive them simultaneously and separate them, so you can double the capacity. And if you know the channel on the downlink, which is a big if, then you can also send signals to these users and transmit separately. So that was called SDMA. And there was a company called Raycom, which started it. It came out of Stanford. I was briefly involved with them as a co-founder, but I stepped out and came back to Stanford. But Marty Cooper was the chairman, and all of you know Marty, and he's been at IMS many times. I spoke to him yesterday. And, but later on, in fact, Raycom made it work in a system finally, in a Japanese system called PHS, which sort of died away. But its application in cellular has been very problematic. I won't go into the reasons. There are many reasons why MIMO, STMA was then coupled with MIMO to say that not just one stream per user, you can have multiple MIMO streams. So that's called multi-user MIMO. So it's part of all the standards, 4G, 5G, and Wi-Fi. In Wi-Fi, it is used, and I think it works fairly well. There's always some issues around that. But in cellular, it's not worked well because of a variety of reasons. I think it needs more work, so I hope the 5G committee, the 3GPP committee will pay attention to that and try and improve its value. The other big thing came is for the so-called massive MIMO. So the idea there was that at high frequencies, the antennas shrink. You lose aperture, you lose link budget. So you need more antennas. So you built an array. And then the only way you can use an array is to form a beam. So beam forming is important to get in a reasonable budget. The 5G, certainly even at C-band and millimetric band, we do that. But, and we also have this arrays also in phones. Your iPhones have them. And but now MIMO layers on top, but the layer on beam, so when you say massive MIMO, it's not massive but MIMO, but just the fact that the beams are involved, we're still talking about layer, 3 or 4 layers. And the gentleman who worked on it earlier, not in context of MIMO, but in context of green technology, meaning using array gain to reduce transmit power, was Tom Mazzetta, now at NYU. So it turns out learning the channel, we have to learn the channel. As a receiver, it's the obvious way of doing it. Transmit pilots, you learn the channel at receiver. And then if the transmitter wants to know it, you've got to send it back or send back some submatrices. This area is quite complicated. If you look at how it's done in 4G and on 5G, enormous amount of complexity in the system. And, but finally, I think it all works, and now we've got to make it work really, really accurately, because we are trying to support very high QAM, and therefore we need accuracies of these channels to about 1 part in 5,000 or so. That takes a lot of work. Pilots and in frequency and time, and I think AI has come into it now. So one of the problems we have today is that the forward channel and reverse channel are not equal. Even in the TDD system, there are lots of other things complicate life. I'll talk about later. So channel estimation is only possible to receive inherently. So you've got to send the data back to the transmitter, which is needed to do the SVD. And fortunately, there's a modulation called OFDM. All of you work with it. And that was a beautiful combination of MIMO and with MIMO. And I think this first marriage in the company called IOSpan, which I started in 1998. So that marriage has not been broken so far. A lot of people are trying to break the marriage of MIMO with OFDM. Not yet happened. Well, MIMO can work with any modulation, with spectrum, with single carrier, but life is very, very difficult. It's very complicated. OFDM is a beautiful combination. And as I said, channel estimation is a very big area, and people spend lifetimes figuring it out and improving it. And so now we're kind of going away from communications to localization. And the core idea there was that if you have an antenna array, and you have single signal arriving at the antenna array, and let's assume it's a planar signal, and let's assume the array was ideal in the sense that everything, all the elements were matched, all the RF was matched, and so on the receive side, what you would do is you would, giving the planar wavefront, you would estimate the signal. And the maximum likelihood method of doing that is technically scan a beam and look for the highest response, and that's your best estimate of the angle of arrival. And so if it was a what about the angle of departure? So it turns out angle of departure is often used. It's used now today in many products because angle of arrival requires the source to transmit something. Of course, you can use radars to get back backscatter, but as a transmitter, it may not be cooperative. So angle of departure is to transmit something towards the thing and look for a response, because it's got to report back to you what it saw. So that's the angle of departure technology at the simplest level. But things get really, really complicated. It turns out there's lots of things that spoil the party here. First of all, is multipart. So multipart changes the signature. The antenna elements are not identical in phase and gain response. The RF is not identical. So in real world, particularly because the multipart elements could be moving, the relationship between the angle of the source and what you see as the receiver is very complicated. So if you want to get really good estimation, you've got to figure out all these things. And to learn that is called array manifold calibration. That takes a lot of work. So this is an area where a lot of work was spent earlier, and I think still the defense uses it. But in communication, we just send pilots, and we don't look at this problem. As the DOA or AOD becomes important, sorry, DOD, the departure becomes important, particularly in the consumer electronics, I'll talk about later, we've got to look at this problem more carefully. Right now, I think we just assume it's a planar wavefront, but when you go to localization from, say, 5 degrees to 0.1 degree, which will go there one day, we need to worry about all these things, and this has plenty of complexities around it. So the other area of antennas is antennas, as you know, are expensive for various reasons because, you know, they take up space, they take up power, and so on and so forth. So how can you synthesize larger arrays with simpler arrays? This has been a very, very large area. I don't think I really contributed to this area, maybe a little bit, but one of the easiest way to do it, and this goes back at least 50 years, thanks to the US Air Force, where you have a single antenna flying in an aircraft, and by looking at the antenna transmission reverse in time, you actually, the antenna is moving, you can take everything together and synthesize an array. It's called synthetic aperture radar. So those days, those were very complex pieces of equipment, but today, with the RF that you build and the tech and the signal and the semiconductor that we have, this has become routine. Now they're flying in LEOsats, and they're probably also flying in drones today. So it's come down to, the applications have greatly increased. There's also something called ISAR. I think there's ISAR is where instead of you moving, the target moves, and you can use that to synthesize the array. It's used by the armed forces a lot. It's also begun to enter consumer products. So it's lots of nice challenges there. Other one is this MIMO radar, where you, instead of having a physical radar like we have in 5G or 4G or in your phones, what it does is you just have N transmitters and M receivers, and by time multiplexing transmit and receive, you can create that green N by N virtual array. Of course, you're time multiplexing there or frequency multiplexing. You have to be careful the channel is not changing. So this has got into auto radars. It's got into products I've seen where it's used in devices in cars to detect any passengers around. So who are they? I mean, are they in the car? I think really to avoid leaving people or babies behind in cars and so on and so forth. So that is becoming also commercialized heavily. The other one is more complicated stuff and multi-mode, multi-port, parasitic kind of technology. We use only one or two antennas, and by active antennas, you're driving with RF, but use parasitic antennas with pin diodes, manipulated pin diodes, and some multi-port chambers to simulate arrays. So there have been some attempts to commercialize this in Wi-Fi. There's a company called Ruckus who's trying to do that, but there's a lot more to be done here. And so this will be also, I think, good frontier for antenna design. And of course, somebody here from NASA, we've been using Earth space rotation for synthesizing arrays, and that, of course, is well known, but I'm sure more can be done. So algorithms for array processing is, again, lots of nice history here. You can take MIMO, which sort of, started around 1992, almost 500,000 papers. So much of work was done. And initially, we tried to conquer a much more complex situation where we don't know the channel and all kinds of things. But after, and initially also my blind side, was that in those days when I talked about mobile networks, I thought real mobility, meaning you're going at 20 or 30 miles per hour in the street or 60 outside, and you got to deal with that channel. But today, almost all the load is shifted to static, stationary, pedestrian. Not very much actually takes place in the car. And so a lot of the assumptions we made 25 years ago and all the complexity has gone away. Today, we're able to, in 5G, get very, very good channel estimates by pinging the system quickly, and then you can use SVDs. And what was a very complex decoding, in fact, impossible to decode perfectly, you can do it today trivially. So a lot of things have become much simpler. This is usually, it doesn't often happen in technology. And then, of course, the DOA and DOD, again, a very long history. And of course, there's things like Capon, music, Esprit, I was in that, behind that algorithm, model fitting and atomic norms. So a lot of going on today. Mostly I see auto radars. And I should mention about Esprit that now there are about 30,000 papers on Esprit, but very few applications. MIMO, and I remember in '91 coming to a conference, and I came to Toronto on business, went to an ICASP and saw 7 parallel sessions in Esprit. MIMO was initially was kind of ignored and rejected, but is now everywhere. So there's some story there, and of course there's lots of literature in signal processing, radars, and sonar literature. Sonar not so much, but there's a lot happening and there's a lot to understand. And of course I never go beyond the system side. But in my companies, I've always had RF groups, and since I know nothing about RF, I have great respect for them. So again, thank you for doing what you do. And finally, I think I would say that AI is being inserted to improve performance, channel estimation, beam management. So a lot going on. I don't really track that area. So I think the big news is there's a mass market working where all this can be used. So whether it's drones or it's phones, it's synthetic aperture radar, because in cellular, Wi-Fi, ADAS and cars. So lots of platforms, satellites, terrestrial, auto, home, phones, smart glasses, hearing aids, to ultra-wideband, Bluetooth, Wi-Fi, cellular, RFID, GPS, V2X, mix of technologies. And I think out of this mixing, platforms, frequency bands, and technologies, mixed and matched will create miracles. And we'll go to a point where we can pinpoint things to within a few millimeters, and that will open up a whole load of applications. So antenna arrays are ubiquitous, it's getting more so, and the market is not one off, or a million off, 100 million off, it's billions off. So huge opportunity for the audience here. So with that, I think I finished, and thank you very much indeed for